chemical equilibria, we'll do an IGCSE, GCSE recap, and then we'll get really into the nitty-gritty to do with case C. So remember, first of all, that this arrow represents that the reaction is reversible, which means it occurs in both a forward and reverse direction. In reversible reactions equilibrium, the forward and reverse reactions proceed at equal rates. The concentrations of reactants and products remain constant. This does not mean they're necessarily equal. The system must be closed, and that means that neither the reactants or products can escape. And that is your definition, really, of a dynamic equilibrium. Remember, adding a catalyst doesn't affect the position of equilibrium. It just means the equilibrium is established faster. Don't forget Le Chatelier's principle, which states that if a change is made to a system equilibrium, the position of equilibrium moves in the direction that opposes the change. And that statement there is incredibly important if we consider the effect of temperature and pressure on the position of equilibrium and fundamentally the yield of either the products or reactants. So if we use this reaction here, which is ethanol reacting with ethanoic acid in a reversible reaction to produce the ester ethyl ethanoate plus water. Now at the beginning of the reaction, clearly you'll have the highest concentration of the reactants of both the ethanol and the ethanoic acid. So their concentrations up here will be high. The concentration of the products will be low because the reaction hasn't started yet. Then as the reaction takes place, reactants react, therefore their concentration decreases, and as their concentration decreases, the concentration of products increases, and then you'll reach a point whereby the concentration of reactants and products remains constant. You'll be familiar with the Haber process, I'm sure. This is the manufacture of ammonia, NH3, and it involves nitrogen gas reacting with hydrogen to produce the ammonia. Make sure that that's balanced, and delta H here is minus 92 kJ per mole. And that's incredibly important, remember, because that tells us that the forward reaction is exothermic, which means the reaction gets hot. So in order to increase the yield of ammonia, that's to increase the yield of product, what do we want to do to the temperature? We want to decrease the temperature. And the reason for that is, according to Le Chatelier's principle, any change you make to the reaction conditions, the position of equilibrium shifts to oppose the change. So by decreasing the temperature, it will favour the direction which increases the temperature. So in this case, the exothermic forward reaction, because after all I said that releases heat energy, the reaction vessel gets hot. So our reason for that is because the forward reaction is exothermic. Sometimes they ask you about compromise conditions. Remember, by decreasing the temperature, despite the fact you're increasing the yield of ammonia, decreasing the temperature has the knock-on effect of lowering the rate of reaction because it means that particles have less kinetic energy. So in the end, we use a compromise temperature of 670 Kelvin because that gives a sufficiently high yield as well as a sufficiently high rate of reaction. Now let's consider the effect of pressure. So again, to increase the yield of ammonia, this is when you need to count the number of moles of gas on each side of the equation. So we look at the large numbers. There's 4 moles on this side versus 2 moles on this side. So to increase the yield of ammonia, we want to increase the pressure. Again, why? Because according to Le Chatelier's principle, the position of equilibrium shifts to oppose the change we've made. So if we've chosen to increase the pressure, the position of equilibrium will shift in favour of the forward reaction because that has fewer moles of gas on the right-hand side. So there are fewer moles of gas on the right-hand side. So the position of equilibrium shifts to the right. Let's consider collision theory and rates of reaction. Well, actually, we don't have the same issue here with an increase in pressure compared with the decrease in temperature. Why? Because increasing the pressure is good because it increases the rate of reaction. So we have no compromise here. But the problem with high pressures is they're extremely expensive and also dangerous because you have to reinforce all the reaction chambers. So instead, we use a compromise pressure of 200 atmospheres, which gives a good balance of high yield, high rates of reaction, but reduces costs and danger. Last up, we have an ion catalyst, which is added. As I've already said, this has the effect of increasing the rate of reaction. It does not affect the position of equilibrium though. It just means that equilibrium is achieved faster. This is a whistle-stop tour of Le Chatelier's principle. Do watch my IGCSE and GCSE videos on the same topic if you're less sure and you want to take it slightly more slowly, because we're now ready to have a look at KC. Now, the equilibrium constant is concerned with concentration. It's really key, you know that. So we're going to be very interested in concentration throughout this video. Kp is a different expression and it's used for when we're dealing with gases and pressures, not concentration. Initially, we're going to determine an expression for Kc. You need to follow these rules. Kc is the concentration of products divided by the concentration of reactants, all raised to the power of the molar coefficient. I promise that's easier than it sounds. So to help us with that, let's take a reversible reaction where hydrogen gas is reacting with iodine gas. Notice that everything needs to be in the same state. You need a homogeneous reaction for this. So they're all in gaseous state, and because it's to do with equilibrium, we must have that reversible reaction. So let's determine an expression for Kc for this particular reaction. Remember, we use square brackets like this to represent concentration. So let's reread our definition. It's the concentration of products. So there's our product in that concentration bracket, divided by the concentration of reactants. So our reactants are both hydrogen and iodine, raised to the power of the coefficients. So let's check the coefficients. 1 and 1, so we don't change this value. The crucial thing here is the 2, and we raise it. So we make a power out of it, which is why this is the final answer. So this is your expression for Kc. The next question we need to ask ourselves is, does Kc have a unit? Because we're obsessed with units in chemistry. And unfortunately, you have to work this out individually for each reaction because it varies. So how to find the unit? Substitute in the concentration unit, which is mole dm to the minus 3, for each reactant and product. So let's take a different reversible reaction. We've got nitrogen and hydrogen reacting to produce ammonia, which hopefully you recognise is the Haber process. Make sure it's balanced. Let's write an expression for Kc. So we want the concentration of products, so that's the NH3 raised to the power of the coefficient, so that's 2, divided by the concentration of the reactants. Again, raise any coefficients as a power. So there's the expression for Kc. Let's work out the units now. So we know we've got concentration unit mole dm to the minus 3, and we've got that little power, so it's to the 2, divided by mole dm to the minus 3 for the nitrogen, mole dm to the minus 3 raised to the power of 3 for the hydrogen. Now we need to cancel this down, so we managed to get rid of this one. This turns into a 2, so let's simplify. So you need to be quite good with your indices here, because it's effectively upside down. We put that little minus there to represent that. And then what do you do with these powers? Well, you have to multiply them. So this requires knowledge of GCSE and IGCSE maths. And then if you're being really good, you just rearrange that a little bit, because the convention is to have the positive number first. But don't stress too much if you don't want to. So we've looked at writing an expression for Kc, working out the units of Kc. Now we're going to actually calculate a value for Kc. So in order to calculate Kc, you want to find the equilibrium concentrations of each reactant and product and substitute these values into your Kc expression. So here we have the Haber process again, and we've been told that the equilibrium concentrations in the manufacture of ammonia are the following: so nitrogen 18.6 mole dm to the minus 3, hydrogen 0.9 and ammonia 1.5. So let's write our expression for Kc again. It's good practice. So there's the concentration of ammonia, concentration of nitrogen, and then hydrogen. So substitute in our values, so we know we've got to do 1.5 squared for ammonia divided by 18.6 for nitrogen multiplied by 0.9 for hydrogen raised to the power of 3 to get a final value for Kc, which is 0.16, and then the same units we calculated before. So that looks like this. Sometimes you're not given equilibrium concentrations, sometimes you're just given starting concentrations. You need to work out the equilibrium concentration by doing the following. You want to use the molar ratio to work out the ratio of each component when equilibrium has been reached. And so if all the volumes are the same or the volumes are not given in the question, then you can just substitute the number of moles you've been given into your Kc because the volumes all cancel out anyway. And I'm writing a little note here as to why you can do that, because the volumes cancel out. If volumes are given in the question, you need to calculate concentration as usual. So remember, in order to do that, you use this formula triangle NCV. So to work out concentration, you do number of moles divided by volume. Remember that volume needs to be in decimeters cubed. The next thing we want to consider is, what does the value of Kc tell us? Well, if Kc equals 1, then it means that the position of equilibrium lies in the middle. If Kc is less than 1, then the position of equilibrium lies towards the reactants. And then, as you might expect, if Kc is greater than 1, then the position of equilibrium lies towards the products. Can we actually alter the Kc value? Well, the first thing to point out is that changing the concentration or pressure has absolutely no effect on Kc. Really important that you're aware of that. And the reason for that is because when you make those changes to the system counteracts the change according to Le Chatelier's principle. So if you increase the concentration of products, the position of equilibrium will shift towards the reactants. And what this does is cause a rebalance of your equation for Kc, meaning that its value does not change. However, if you change the temperature, Kc is altered. So the answer here is yes, if you change the temperature. So please, please, please be aware that concentration and pressure changes have no effect on Kc, but changing the temperature does have an effect. And why is that? When you change the temperature, the system acts to counteract the change in temperature. And I'm going to use a quick example to show you how this works. So going back to our trusty old Haber process again. The forward reaction here is exothermic, which remember means it gets hot. So we favour the forward reaction by lowering the temperature. So you need to check out my other video if you're not happy about that. So we'll grab that Kc expression for this again. So let's consider if we increase the temperature. Remember, in this particular reaction, because the forward reaction is exothermic, it means that if we increase the temperature, the position of equilibrium will shift to the left. So what does that do? Well, it increases the concentration of our reactants, and therefore this number here gets bigger, meaning that Kc decreases. So you do have to juggle this. If we consider if we decrease the temperature, this time the position of equilibrium shifts to the opposite, so to the right hand side. So therefore we make more ammonia. So the ammonia concentration increases, which means this number gets bigger, and therefore Kc increases in value. One last thing is to point out that adding a catalyst has no effect on Kc value. And that's because it speeds up the forward and reverse reactions equally. Now, in order to calculate Kc, you do need to be able to calculate the equilibrium amounts, so the amount in moles of reactants and products, given the initial amounts of reactants, and honestly the best way to do that is using what I call a rice table. So I'm going to show you how to do that here. So in this question, 1.5 mole of NO are mixed with 1 mole of chlorine, and the mixture is left to reach equilibrium at a given temperature. The equilibrium mixture contains 0.35 moles of NaCl. Calculate the amount in moles of NO and Cl2 in the equilibrium mixture. So your first step with this is to write out your balanced symbol equation. And now we use rice to help us work methodically through this. So R stands for your reaction equation, so that's what I'm going to label that as being. Then we have ICE. Underneath I'm just going to list what RICE stands for. So R is your reaction equation. As you can see, I've already written that in the table above. I stands for your initial moles, so what you start with. C stands for your change in moles. And E stands for your number of moles at equilibrium, so your equilibrium moles. And now all you have to do is start working your way through the wording of the question to fill in the table. So we know we start with 1.5 moles of NO. Chlorine we start with 1 mole. And because the reaction hasn't gotten underway yet, we start with 0 moles of our product. What else do we know from the question? The equilibrium mixture contains 0.35 moles of NaCl. So it's now straightforward for us to work out what happened. What's our change in moles? Well, from our initial to our equilibrium moles, we have gained 0.35 moles. And that's so helpful because now we can work out how many moles we have lost of the NO and the Cl2. Just check the mole connection. Because remember, when we do mole calculations, we're able to carry across numbers. So if we have gained this much product, it means that we have lost the same amount of reactants. So that's minus 0.35 moles. So 1.5 minus 0.35 becomes 1.15. And then just be careful here with the mole connection. It's 2 to 1. So in terms of how much we've lost here, we just need to make sure we halve that number. So it's minus 0.175 moles. And therefore, to work out equilibrium moles of chlorine, just do 1 minus that number you just found. So that's 0.825 moles. So you've done all the hard work. We're now going to use this question to actually find a value of Kc together with the units. So here a mixture of carbon monoxide and hydrogen reached equilibrium in a container of volume 250 centimeters cubed at temperature T. At equilibrium, the mixture contained 0.34 moles of carbon monoxide, 0.19 moles of hydrogen, and 0.061 moles of methanol. Find Kc and give the units. Right, they have told us the equilibrium moles, so we don't need to use the rice table here because they've done that for us. We're going to start by writing our expression for Kc. So remember, that is the concentration of our product, which is methanol, divided by the concentration of the reactants, making sure you raise any of them to the power. So that 2 came from here. After all, we need the concentration, so we're going to use this formula triangle in order to find the concentration. So our concentration of methanol, using that formula triangle, is the number of moles, 0.0610, divided by the volume, which we were told was 250 centimetres cubed. Just be careful, that needs to be in decimeters cubed, which is why I'm dividing by 1,000. Let's do the concentration of carbon monoxide. Very similar. There we are, dividing it by its volume again. And then finally the concentration of hydrogen, 0.19 moles. Okay, perfect. So we'll steal that expression. Let's substitute in all our values. Remembering to square the concentration of hydrogen based on the Kc expression we worked out. So Kc equals 0.311. And then lastly, the units. Again, we're using the expression of Kc, substitute in our concentration units, cancel them down. So our final answer is 0.311 moles to the minus 2 dm to the 6. When a 0.218 mole sample of hydrogen iodide was heated in a flask of volume V, the following equilibrium was established. The equilibrium mixture was found to contain. Calculate the number of moles of iodine and the number of moles of hydrogen iodide in the equilibrium mixture. Draw out a Rice table then. So here's our R. So we know we started with 0.218 moles of hydrogen iodide. By definition, we won't have any of our product at the beginning. The mixture was found at equilibrium to contain 0.023 moles of hydrogen, which means we've gained 0.023. Check the mole connection, it's 1-to-1, so again, we can write the same for the iodine. And now, what about the change in moles of our reactant? Just check the mole connection, it's 2-to-1, so we need to double that number here. Obviously, the reactant gets used up, so that's why we're minusing that number. So that's 0.172. So we're ready to just input those numbers here. So calculate the number of moles of iodine at equilibrium. We can see it's 0.023 moles. The number of moles of hydrogen iodide is 0.172 moles. Write an expression for Kc. So there's our concentration of our products multiplied together, divided by the concentration of reactants raised to the power. State why the volume of the flask need not be known when calculating a value for Kc. All you have to write here is because the volume cancels in the Kc expression. And you can see that here. Calculate the value of Kc at 700 Kelvin. We'll steal that expression. You don't need to find the concentration, you can just use the number of moles at equilibrium here. Substitute those in. And then calculate the value of Kc at 700 Kelvin for the equilibrium. This equation is the opposite way round. You could plug all your numbers in. You could write a new Kc expression, plug your numbers in, but honestly the easiest thing to do here is just do 1 over your answer from before. It's the same, to get 55.9.